So today we are going to discuss what is called the it's named after somebody called Kakeya. Kakeya problem or Kakeya's problem. Okay, the original formulation of the question was to construct a set in R2 which contains a unit line segment in every direction. So you want to construct a subset of R2, and obviously you can take all of R2 and it contains everything, all unit line segments in every direction. But the goal is to construct a set in R2 of small size. The question of how you measure the size is a different matter, but you want to construct a small subset. So what is an obvious construction? How would you construct a subset in R2 which contains a unit line segment in every direction? Take a circle of radius half. If you take a circle of radius half, diameter 1, obviously it contains through the center, if you take each diameter, that's a unit line segment in every direction. What is the area of this? It's pi by 4. Now the real question is how small a set can you construct? Let's think of it as small in some integrable sense, so that then how small, what is the smallest area that is possible for a set that contains a unit line segment in every direction? Okay, sometime after this obvious construction, if you look up Kakeya problem in Wikipedia, you'll see a little very nice animation on one corner, which is the so-called deltoid construction. So what is a deltoid? You take a circle of diameter 3 by 2. So that is the big circle. So diameter is 3 by 2. And then inside that you place a small circle of diameter half. Put a circle of diameter half inside it. And tangential to it. What I mean is that it's touching the circle inside. Now take any one point on the inner circle and rotate this small ball along the wall of the bigger circle around. So and look at the path that is the locus of this point as the circle rolls on the inner ball. What you will get is what is called a deltoid. It will be something like this. It will touch the circle exactly at 3 points, because the length, the perimeter of the inner thing is the outer thing is 3 times the inner thing, pi into the diameter, right? Diameter of the outer thing is 3 times, so it will touch it exactly in these 3 places. And now what you can do is you take the tangent at every point. So this thing is called the deltoid, and this deltoid is a Kakeya set. So any such set is called a Kakeya set. and we are trying to construct a Kakeya set of as small size as possible, as small area as possible, let us say. So, now you draw the tangent at every point inside the, so this is the tangent here. So, take all these tangents and take unit line segments along the tangent. You will see that all those unit line segments are actually contained inside the deltoid, and as the tangent moves along the deltoid, it takes all possible directions. So, slide that tangent along the deltoid and take unit line segments on the tangent, and that will always be contained inside the deltoid. Of course, which unit line segment to take, I do not know. I think it can be analytically described, but I do not know the answer. Obviously, at this end you will take the unit line segment which is completely on one side of the point of contact, and at points here I suppose you take it roughly symmetric on either side. So, I do not know the analytic expression for that, but this is a construction. It turns out that the deltoid has area pi by 8. So, then the question is, what is the best that you can do? How small can you make the area? It turns out that by refining the deltoid construction, there is somebody called Besikovich has constructed a couple of centuries ago, I think, I do not know when, a Kakeya set of measure 0. Measure 0 roughly means area 0. What does that mean? Okay, let's. So, it is a generalization of the deltoid construction, in the sense that the idea is you can slide the line segment up and then make room for it by sliding it back, so that it does not occupy much area. So, here we are keeping the position of the line segment, the center of the line segment intact, and rotating the thing. That is why it is occupying so much space. In the deltoid you are sliding it back and forth, and therefore you are able to shrink it somewhat. It turns out you can iterate that idea and make the line segment move back and forth so often that the area becomes kind of, in a limiting sense, 0. Okay, let me just explain to you what this measure 0 means. What is a measure 0 set? I will describe it in real numbers, and it is a generalization to R2 or Rn anywhere. A measure 0 set is a subset. Okay, if you take a subset S of R, subset of real numbers, we can talk of the measure of that subset. Okay, it's also called the Lebesgue measure. Is denoted by mu s, is defined in a is the limiting sum of the smallest open cover containing S. Okay, it's all technical jargon. Let me try to explain what I mean by it. So on the real line, suppose you're given some set. So okay, let's start with maybe a simple example. So this is 0 and this is 1. What should be the measure of the interval 0, 1? It should be 1. That is the length of the interval. So mu of the interval 0, 1 is 1. What should be mu of the open interval 0, 1? That is also 1. because throwing away the two endpoints shouldn't make any difference to the length of the interval. The actual content, throw away finite number of points, it shouldn't make any difference. Similarly, if you take the set, I am trying to explain this definition through some examples. Take the set 0, 1 and drop, let us say, the points 0.1, 0.2, say up to 0.9. So you have thrown away 9 points from the interval. What should be the measure of this set? So suppose S is this. What should be the measure of this set? It should be still 1. Okay. Why? Finite number of points. But can we try to can we try to fit this definition that I was trying to write down here to define the measure of the set? I want I want an open cover for this set. What do I mean by an open cover? An open cover is a collection of open intervals. For instance, an open cover that covers the set S is let's say something slightly less than 0, or just take -1 to 0.1, and then something slightly less than 0.1, we can say 0.09 to 0.2, 0.19 to 0.3, and so on. The last one can be 0.89 to something more than 1, let's say 2. Okay, so this is an open cover for the set S because the union of these intervals covers the set S. What is the length of this open cover? The length of the first, so that's the sum of the lengths of these open intervals. Okay, the size of the open cover. The size of the open cover is this. In this case, you only finitely many open intervals there. So the size is just the sum of the sizes. In this case, it's 1.1 plus all of them are 1.1. I deliberately took it like that. So there are 9 of these. And the last one is a bit large, is it? 1.11. And the first one is 1.1. Oh, this is also 1.11, no? Yeah. Oh, these are 0.11. Oh, okay, all the intermediate ones are 0.11. So it's only the first and the last ones are a little large. Of course, we didn't have to keep it like that. We could have taken this to be minus 0.01 and the last one to be 1.01, in which case they would all be of length 0.11 each. Hey, no. Is that right? Yeah. So what is the sum of these? 1.09. So that is an upper bound on the measure of the set. But I can find a smaller open cover. Instead of taking a 0.01 here, I could replace this 0.01 by an epsilon. So here I have an epsilon. Instead of 0.9, I'll have 0.1 minus epsilon, and here 0.2 minus epsilon, etc. 0.9 minus epsilon. In the end, I'll have 1 plus epsilon. Right? And what does that give me? It gives me something that's of length. The last one was 2 epsilon, right? Okay, solid. So that gives me an overall length of 0.1 plus epsilon plus 0.1 plus epsilon 9 times. The last one is 0.1 plus 2 epsilon. So the overall thing is 1 plus 1 plus. something times epsilon, 9 times or 10 times epsilon. So, for every epsilon I have an open cover such that the sum of the lengths of the open intervals in it adds up to 1 plus 10 times epsilon, and the limit exists because if I let epsilon go to 0, then for every epsilon that is an open cover, and in the limit I have an open cover whose length is 1. Okay. So, that is only the upper limit. If you want to define the measure correctly, you will also have to talk of a lower limit. You find a cover from within the set. Okay. What is the smallest cover that is contained inside the set? And if both the limits exist and they are equal, that is the upper and the lower limits exist and they are equal, then you say that the set is a measurable set. It turns out that all subsets of real numbers are not measurable sets. Okay. That is a very rough definition of what Lebesgue measurable sets are. The entire area is called measure theory, where you want to study various properties of measurable sets and analyze them. What is a measure 0 set? If you can find an open cover whose total length is bounded by an epsilon, for every epsilon greater than 0 I can find an open cover such that the sum of the lengths of the intervals in that open cover is bounded by epsilon. Then I know that the upper limit is 0, the lower limit anyway I can always find a cover inside it which is the empty cover which is of length 0, and that gives me a measure, that is a measure 0 set. So, here what is an example of a measure 0 set? If you take a finite number of points, any finite subset of R has measure 0, because I can always put an interval of length epsilon around each point in that finite set. So, suppose there are t elements in my set, how many intervals have I put? T intervals each of length epsilon, so t times epsilon, as epsilon tends to 0, that tends to 0. But funny things happen. Okay, you can even prove that every countable set, every countably infinite set, every countably infinite subset of R of the reals has measure 0. How do I prove that? Not difficult. So, what you can do is, so let us say S is a countably infinite set. So, because it is countably infinite, I can put it in 1-1 correspondence with natural numbers, and I can think of the set as small s1, s2, etc. This is a countable infinite subset of real numbers. What I can do now is define the interval I sub I, which is, let us say, Si minus epsilon by 2 power I, Si plus epsilon by 2 power I for all I. So, I have put one little open interval around each of the points. So, the collection of these I sub i's is an open cover for my set S. What is the sum of the lengths of these intervals? That is 2 times epsilon by 2 power I summation, I goes from 1 to infinity, okay, and that is epsilon, or whatever, 2 epsilon maybe. The first term in the series is 1 plus, so it is 2 epsilon, okay. Maybe I should have taken 2 power I plus 1, it does not matter, right, then it is epsilon. And therefore, this is a measure 0 set. So, every countably infinite set is a measure 0. So, when he proves that a Kakeya set, when he constructs a Kakeya set of measure 0, it is not like something that is impossible, because infinite sets can be of measure 0. Not only countably infinite sets can be of measure 0, there are uncountably infinite sets also which are of measure 0. I do not know if you have seen this. Do you know, have you heard of such a construction? If you have seen something like this before? Cantor set. Yeah, I mean there are some of you who have learnt all these things. So, let us just quickly I'll just mention that because I'll anyway have to tell you a little bit about Cantor sets at some point today. So what is a Cantor set? So what you do is you start with the open interval and it's defined by a kind of iterative process. You remove the middle 1/3 of this interval. So now you're left with two intervals, 0 to 1/3 and 2/3 to 1. For each of the two intervals, remove the middle 1/3 and repeat ad infinitum. What is left is the Cantor set. Remove the middle 1/3 of each interval at the ith stage. So you'll do this for I going from 1 to infinity. You'll do this. In the end, you'll output S. S is the Cantor set. So it's easy to argue that the Cantor set is a measure 0, because if it has a non-zero measure, you must be able to put some open interval inside it, but you're removing the middle 1/3 from every interval at every stage. So you can figure out that it cannot contain any open interval at all, so it must be a measure 0. Okay, so its measure 0 is kind of forced by this construction, and the simple reason why it's an countably infinite set is a very nice argument, because you can do a ternary expansion of all the numbers from between 0 and 1. So if I do, every number between 0 and 1 can be written as this infinite ternary expansion where AI's come from 0, 1 and 2. It turns out that this process of removing the middle 1/3 at every stage amounts to ruling out any of these AI's from being 1. So the Cantor set S consists of precisely all the numbers of the form 0.A1, A2, etc., where the AI's come from either 0 or 2. 0 is 0.0000 and 1 is 0.2222, all 2's. And this set clearly is countably infinite. Why is it countably infinite? Because each of the AI's has two choices and its cardinality therefore is 2 to the power the cardinality of natural numbers. That is the same cardinality as the set of all subsets of natural numbers, which we know has the same cardinal number as real numbers. Okay. So its cardinality is that of real numbers, but it is of measure 0. So measure 0 sets can be huge, and therefore, I mean, this is not unbelievable that you have Kakeya sets of measure 0. But what is the Kakeya problem, which is a long-standing open problem? Something of Kakeya's original intuition, what he conjectured was, and it turned out to be wrong as proved by Besikovich, he conjectured that if a set in R2 contains a unit line segment in every direction, then it cannot be of measure 0, and that was proved false. Okay. But the modified conjecture is that the dimension of the set, and so there is another notion like measure, there is another notion of dimension of arbitrary sets. There are two notions of dimension. I will explain one of them to you because it is kind of easier to understand. There is something called the Minkowski dimension of a set, there is something called the Hausdorff dimension of a set. The modified conjecture is that the dimension of the set must be 2. So it must be like a 2-dimensional set if it contains a line segment in every direction. And it was proved, I don't know whether by Besikovich or who, for the 2-dimensional case. You can formulate the same problem for higher dimensions, and there it is still an open problem. And that is what motivates what we are going to discuss today, because that is a long-standing open problem. somebody suggested we should first look at the finite field setting. And in the finite field setting, the modified conjecture can be proved easily using the polynomial method. So that's what we are coming to. Okay. So let's spend 2 minutes discussing what is the dimension of a set. Okay. So firstly, the Kakeya sets in higher dimension is exactly the same. So in Rn, you want to construct a subset of Rn which contains a unit line segment in every direction. Okay, and such a thing is called a Kakeya set. And what Besikovich did in R2 can be generalized to Rn as well. Something that's like, sharp in every direction, but it has measure 0. And that will be able to accommodate a line segment in every direction. It's a kind of limiting construction. It's a limiting construction of the deltoid idea. Okay, let me spend a few minutes explaining this notion of Minkowski dimension. So take a subset S contained in Rn. So let's just focus on bounded sets. So let S contained in Rn be a bounded set. So a typical bounded set for us is the unit cube in Rn sitting in the first quadrant. How do we describe it as a set? So let's say S is 0, 1 to the power n, sorry. And this is n times. So that's the Cartesian product of 0, 1, n times unit cube. Okay. Intuitively, what do we understand by the dimension of the unit cube? It's n dimensional. Right? It fills up all the axis. Okay. It's shrunk, but it's n dimensional. Okay, so the way the Minkowski dimension is defined is for each delta what we want is let n sub delta S denote the smallest number of cubes of side delta required to cover S. So cover in the same sense. What is the smallest number of cubes that are required to cover S? In all, 1 by delta to the power n. So I know that n sub delta 0, 1 to the n is 1 by delta to the power n. Okay. So intuitively what I am thinking of is that this n should somehow capture the dimension. Okay, for analogy, let's say, suppose you take just along the x-axis the unit line segment. So let's say 0, 1 is your set S. In other words, 0, 1 cross 0 cross 0 cross 0. So only along the x-axis you're actually moving it all, you're 0 on all the other axes. So this is just a line, right? What is the dimension of a line? It's one dimensional. How many cubes do I require to cover this set, let us call this set S0 or S1. What is n sub delta of S1? How many cubes do I require? I just need to place these cubes are n dimensional cubes, but to cover this line segment I need to place 1 by delta of them along the thing. So I need just 1 by delta of them. So intuitively what seems to be happening is the exponent that is sitting up here should be capturing the dimension, but I also need to be arithmetically be able to get rid of the 1 by delta. So you define the Minkowski dimension, let us call it the m dimension m of S as the limit as delta tends to 0 of the log of n sub delta S divided by the log of 1 by delta. So you can look at these two examples and you kind of just you can just convince yourself that it's at least capturing the dimension, intuitive dimension of these two things. There is one problem could be that this limit doesn't exist, right? But then it will have an upper limit and a lower limit, and they are called the upper and lower Minkowski dimension. There are sets for which the limit doesn't exist. So those things don't have a Minkowski dimension. They only have an upper and lower Minkowski dimension. Now, yeah, just one more small point. If I take, for instance, a curve like this in R2, if I take a curve, what should be the dimension of the curve? A curve is one dimensional. It's like a line, isn't it? A curve is one dimensional. Now, however, it may be shaped, the curve may be shaped like this, but it's still one dimensional. How does this definition capture that fact that it's one dimensional? So let's try to apply this definition. We are working in R2. So in R2 the cubes are 2 by 2 boxes, two dimensional boxes of side delta. So we will be putting little boxes of side delta here, covering everything, of course. Okay. Now what might happen is that if you choose a large delta, you may be able to cover with a single box oops. Sorry, what is the point that I want to make is no, okay. Now let me not. The point that I want to make here is already captured by something much simpler. Okay. So suppose instead of 0, 1 to the n, I look at a box of a larger n dimensional box. Let's say it's something that's of the form 0, 100 to the power n. Suppose this is my set S. The number of little delta side cubes that are required to cover this is much larger, isn't it? What is it? It is 100 by delta to the power n. So my n delta S is much larger. So what is the dimension of such a set then? The dimension of such a set would be log of 100 by delta to the power n divided by log of 1 by delta. Notice that 100 doesn't make a difference, and that's the reason why we are looking at delta tending to 0, because you get n as a multiplicative factor anyway, log of 100 by delta is log 100 plus log 1 by delta, and log 100 by log 1 by delta anyway goes to 0 as delta tends to 0, because 100 is fixed. So if you dilate an object, you don't change its dimension by some factor if you dilate an object. That's the reason why you divide by log 1 by delta and let delta tend to 0. Okay, so this explains Minkowski dimension, and there's just one small point I wanted to make about the Minkowski dimension, that it can be fractional. There can be subsets of R which have Minkowski dimension half, something more than 0 but less than 1 is possible. So we take the Cantor set. It's a nice little exercise to check that the dimension of the Cantor set, Minkowski dimension of the Cantor set, is something like log 2 by log 3. So this log is, it depends on what you want to think of this log as. Actually, if you think of it as log to base 2, probably the original definition meant it to be log to base e, but that shouldn't matter because that's anyway multiplicative factor here, isn't it? Yeah, so the base doesn't matter. So it's log 2 by log 3. That's the Minkowski dimension of the Cantor set. It's a fractional quantity.
So in the definition, is it in the denominator, is it log of 1 upon 1 by delta, or is just log of 1 by delta?
Log of 1 by delta. Oh, sorry, I made a mistake here. Yeah, but I should write log of 1 by delta. Okay, so what is the Kakeya conjecture? And this is considered one of the major problems in the Kakeya conjecture, or problem, or whatever you want to call it. Conjecture is that for all n, every Kakeya set S contained in Rn has Minkowski, and there is another notion which is that of Hausdorff dimension, which I am not discussing because it is more technical, and anyway we are not going to spend time on the Euclidean version. Both the Minkowski and Hausdorff dimension is n. So in some sense, probably Kakeya's intuition, if you translate it, he meant that it must be in space filling in a certain sense. It has to have full dimension. Okay. It's obvious that for any bounded set, the Minkowski dimension is bounded by n. You take any subset S of Rn. What is a bounded set? You can always put it inside a large enough box. You can always put it inside 0L to the power n for a large enough L. Its Minkowski dimension has to be bounded by L, because a cover for the box is a cover for, it's an upper bound for n delta S.
As these are like the definition of Kakeya set is that in every direction there should be a line segment. So shouldn't it intuitively have a dimension in any way?
What do you say about the Cantor set? It's got uncountably many points in some sense in both directions. So on the line, how would you interpret this? When you have a countable set, it has points in, if you anyway, people, so it's a technical statement, and the best bound that people have achieved is for the Minkowski dimension as well as the Hausdorff dimension is n plus 1 over 2. Okay, for n equal to 2 it's settled. For n equal to 2 it's known, it's true. For the real problem is for n greater than or equal to 3. For n greater than or equal to 3, this is the best that's known, n plus 1 over 2 is the best that's known. So there is a, if you go to Terry Tao's blog, it's called What's New, I think. There is a very nice post, one large post on the Kakeya problem and the solution for finite fields, which we are going to discuss right now, right away. So now we are ready to start with the finite field version. So sometime in 1999, is a combinatorialist or whatever mathematician called Wolf. He conjectured or defined Kakeya sets for finite fields as follows. Okay. This is a natural definition. You say that a subset S contained in Fq power n, where Fq is any finite field, is a Kakeya set if it contains a line in every direction. Okay, what does that mean? As we explained last time, a direction is a vector v in Fq power n minus 0, a non-zero vector v that gives the direction, and it passes through a point A. So you take a point A. So when you say there is a line in every direction, for every direction v in Fq power n minus 0, of course, there exists an A in Fq power n such that this set A plus t times v, where t belongs to Fq, is contained in S. So this is a line through the point A in direction v. Okay. This is a kind of combinatorial notion of line in the finite field setting. And the conjecture is Wolf's conjecture that cardinality S must be some constant times q power n, where A depends on, could depend on n, or A does not depend on q, A is independent of q. It can depend on n, but it should be independent of q. This conjecture was motivated by certain lines of attack on the Kakeya problem. The people who proved this had a very combinatorial approach to the problem. Okay, they looked at a discretized version of it and somehow managed to generalize it, and trying to push that particular line of attack, at least this person Wolf conjectured that one should be able to solve this problem first before making progress, using the same approach on the general problem. And what we are going to describe is the solution using the polynomial method, which Dwyer obtained in 2008. It's a remarkably simple application of so this is Dwell's solution sometime in 2008. Okay, his solution is that S contained in Fq to the n, if S is a Kakeya set, then cardinality S is at least 1 by n factorial times q power n. So let's prove this and then we'll see some more things about problem. We already know all the little things that are required to prove this. So the proof is by contradiction, as you can guess. So suppose not, okay. Suppose cardinality S is strictly less than for a Kakeya set. What should we try to do? If you have a small set, you should be able to put a polynomial through it. Okay. There's one small thing we need to note about this. That is, q minus 1 plus n choose n is greater than or actually greater than q power n by n factorial. Why is that the case? We have already seen something like this, no? This is you have n factorial in the denominator, n plus, okay, write it as q plus n minus 1, q plus n minus 2, etc. up to q plus up to just up to q, and then q minus 1 factorial, which cancels with the q minus 1 factorial here. And there are how many terms are here in the numerator? There are n terms in the numerator, and so that's clear. So if cardinality S is less than q power n by n factorial, I know cardinality S is less than q minus 1 plus n choose n. So there is a polynomial of degree at most q minus 1 that I can put through it. So there is a non-zero polynomial let's call it g x1 to xn over fq of degree at most q minus 1, such that let's call it, let's say degree d, which is at most q minus 1, such that g of a bar is 0 for all points a bar in S. Okay. And now we want to use the fact that the Kakeya set contains a line in every direction. I want to use that fact. How do we use that? That it contains a line in every direction. Oops. No, That's not what we, so this is true for every direction. That's what we did in the joints problem. That was different. So here it's different, slightly different. Okay. So what we know is that for every direction V in f q power n, let me write V bar. Okay. There exists an A bar in f q power n such that A bar plus T V bar T in f q is contained in S. Sorry, I just repeated what is already there. This just means G of A bar plus T V bar is 0 for all T in f q. Right. Now it's a degree D polynomial, as you just said. So this is, if you think of T as an indeterminate, this is a univariate degree D polynomial. Right. So let's write G of A bar plus T V bar exactly as we did last time as H of A bar V bar of T. It's a polynomial in one variable T. Okay, what does this look like? When I expand out, no, we won't do that. I'll just describe the, when you throw in T, what is the highest degree T that is possible here? D. D is the total degree of this polynomial. So the highest degree in T is D. So you have a T power D, and what is the coefficient of T power D? All the degree D monomials of G. Right, so G itself I can write like this. See, G I can write as GD plus GD minus 1 etc. plus G0, where GD is the homogeneous degree D part of G, etc. GD minus 1 is, take all the degree D minus 1 terms, that is the homogeneous degree D minus 1 part of G, and so on. G0 is the constant term. Okay. So GD is the degree D homogeneous part. I know GD is non-zero because G is a polynomial of degree D, it has a degree D part in it. Otherwise its degree would have been D minus 1, I would have called that as D. So you have T power D times GD of V, isn't it? So when you expand this, in every degree D term I should be taking this part. That means I won't be taking the A part, only then I will get maximum degree possible, plus the other terms. Let me write it as order T to the D minus 1. This notation means that it's degree D minus 1 and lower. So that's what my polynomial H A bar V bar T looks like. Okay. And I know that, okay, let me erase this part. So GD I know is the homogeneous degree D part, I've already explained that to you. Okay, let me erase this also. This is the homogeneous degree D part of G. What I know is that H A bar V bar T is 0 for all T in FQ. So what can we say about H A bar V bar? It's a polynomial of degree D which is at most Q minus 1, and it's vanishing in Q points because the field has Q points in it. It must be identically 0, it must be the 0 polynomial. implies H A bar V bar is identically 0. Identically 0 means what? Every coefficient is 0. In particular, GD of V bar is 0, which means GD of V bar is 0. So, GD of V bar is 0 for every V bar. Is that possible? How many? It's a degree at most q minus 1 polynomial. GD is a degree, it's a non-zero polynomial of degree at most q minus 1. I know that cardinality of, let's call it points B bar and FQ bar n such that GD of B bar is 0 is bounded by D times Q bar n minus 1 by the Schwarz-Zippel lemma. This is less than or equal to D is Q minus 1 at most, Q bar n minus Q bar n minus 1, and Q is at least 2, Q is at least 2. And n is also at least, I mean n equal to 1 we are not looking at. So if Q is at least 2, this, but this is vanishing in all directions. That's Q bar n minus 1 if you leave out the zeros direction. It's vanishing in Q bar n minus 1, and this has to be at most Q bar n minus Q bar n minus 1, which is strictly less than Q bar n minus 1. That's a contradiction. GD cannot have that many zeros. It can't vanish in all the V bars. Okay. It cannot vanish at all the V bars. Let's just spend a moment when I said all directions other than the all zeros vector. What if we include the all zeros vector as well? Does this make a huge difference? It doesn't, because if V is all zeros, T times V is anyway all zeros. So this is just a single point, and I know that S is a non-empty set, so obviously it contains a line in that trivial sense. Okay, so V bar equal to 0 is not a problem at all. Yeah, I mean anyway we know that the degree D homogeneous part is going to vanish at the all zeros point anyway. Any homogeneous polynomial doesn't have the constant term, no, it is only degree D terms. If I put all the variables equal to 0 anyway, it's going to become 0. So this is actually true for all V bar and FQ bar n. I'm sorry, so it's much easier to argue than that. It's enough to say that it is less than Q bar n, that's enough. So it's a remarkably easy proof that Wolff's conjecture is true. It took a long time to prove it, though. You can say that there are probably people who are stuck with a certain direction of reasoning coming from here, and nobody thought it would be this simple. Okay, so what is what kind of Kakeya sets can you construct in the finite fields case? I'll show you an interesting construction. of Kakeya sets. And then we'll see that there is a gap between the solution of Dwyer and the construction, and then see how to bridge the gap between the two. Kakeya set construction. In FQ power n. So I'm going to discuss the case only when Q is odd. The finite field is the characteristic of the finite field is odd prime. Okay. Q is not a power of 2. Okay, we are going to construct S contained in FQ power n such that cardinality of S is at most Q power n by 2 power n minus 1 plus some things which plus an order Q power n minus 1. So you can see that the gap is pretty large between Dwayer's solution and this. But we can improve the 1 by n factorial to 1 by 4 power n very easily. We'll discuss that. And the current best lower bound is 1 by 2 power n times Q power n. So it's nearly the same as the upper bound. So this construction is pretty easy. Let's discuss this. Okay, so let V bar be a direction such that Vn is non-zero. We'll consider directions where Vn is non-zero. And just a distraction, let's forget that. A direction is a vector in FQ power n. If I set the nth coordinate of the direction vector to 0, I have Q power n minus 1 choices. So I can anyway take through the origin each such direction and add how many points do I need to add to the Kakeya set if I yeah, just add all those points. So I can always let S prime be all points of the form A1, A2, An minus 1, 0, Ai in FQ. Okay, this is a set cardinality S prime is exactly Q power n minus 1. So I'm going to add this set S prime to my S anyway. So I'm going to increase its cardinality only by Q power n minus 1, and this contains a line in every direction V where Vn is 0, because it contains all such points anyway. Because once you put such a direction, any multiple t times V will also have the nth coordinate as 0. So that is part of this order Q power n minus 1. So it's enough to worry about directions where Vn is 0, Vn is non-zero. It's enough to worry about directions where Vn is non-zero. Vn is non-zero, I can as well assume Vn is 1, because anyway in t times the vector V, all other non-zero values will be accounted for. Okay. So we are looking at V1, V2, Vn minus 1, comma 1. Okay. So we are looking at only such directions in FQ power n. The set S is defined as follows. It's all points of the form V1 square by 4 plus V1 into T V2 square by 4 plus V2 into T Vn minus 1 square by 4 plus Vn minus 1 into T, and the last coordinate is just T. So, we are going to have the Vi's coming from FQ and T also coming from FQ. If I just look at it, a crude upper bound for S is there are n minus 1 Vi's, and that's q power n minus 1 choices. There are q values that T can take, that's q choices, that looks like q power n. That's stupid because that's taking the entire FQ power n. But we are going to bound this set. There are going to be many things which are the same. Okay. Let me erase the last two parts. So, in order to bound this, we need to use some properties of finite fields. Okay. So, we look at say Vi square by 4 plus Vit plus T square. What is this? Vi by 2 plus T whole square. By the way, note what do I mean by V1 by 4? When V1 is an element of FQ, why is V1 square is an element of FQ? That's fine because I am multiplying two elements of the finite field. What is 1 by 4 in a finite field? Because Q is odd, 4 is an invertible element. 4 is just the identity added to itself 4 times, right? 4 is 1 plus 1 plus 1 plus 1. Okay. So, 4 is an invertible element, therefore 1 by 4 makes sense. And similarly 1 by 2 also makes sense because Q is odd. And that is why this construction works only when Q is odd. Okay. So the square of the last coordinate plus any other coordinate is a perfect square. So, this is the value of the ith coordinate for 1 less than equal to I less than equal to n minus 1, and this is the square of the last coordinate. If I add the two, it is a perfect square. It is a perfect square in FQ. How many perfect squares are there in FQ? How many elements in FQ are perfect squares? We will argue that only half of them can be perfect squares. If we can argue that, then we are done. Okay, we will need to argue that. So let us call it a claim. Let me write it down as a claim, and then we will first let us see that once the claim is proved, then we are done. Claim is that number of perfect squares in FQ is q by n minus q plus 1, is exactly this much. That is, if you leave out 0, 0 is a perfect square anyway. If you leave out 0, there are q minus 1 elements left. Q minus 1 is an even number because q is odd. Q minus 1 by 2, that is exactly half of them will be perfect squares. So, this is like close to q by 2, right? Essentially like q by 2. So, let us complete the proof and then we will prove the claim. So, of these elements there are only q by 2 perfect squares. Now, how do I get the bound using this fact? So, the last coordinate I can choose any way I like. T can be chosen and has q choices. Now, V1 has to be chosen such that I shouldn't say V1 has to be chosen such that V1 square by 4 plus V1t plus t square has about q by 2 choice values. The number of distinct values that V1 square by 4 plus V1t plus t square can take is at about q by 2. Only so many distinct values it can take, which implies V1 square by 4 plus V1t has only q by 2 distinct values given t. Once given t, this has only so many distinct values. So, what is the total number of distinct values? It is about q by 2 to the power n minus 1 multiplied by q, and that is precisely the bound that you have there. It is strictly speaking this quantity q minus 1 by 2 plus 1 whole raised to the power n minus 1 multiplied by q. But we are thinking of q as being arbitrarily large, okay, and that is the reason why we are writing it like that. The only term that matters is the coefficient of q power n. So we need to prove this claim and then we are done. This is the Kakeya set. The Kakeya set is S union S prime is the Kakeya set. Why does it contain a line in every direction? That we haven't seen. The S prime part contains a line in every direction where Vn is 0. When Vn is not 0, what is the line that it contains? By construction, no? You take, what should I take A bar to be? If you give me a direction V bar, I will take A bar to be V1 square by 4 plus V1, no? What is T times V1 square by 4, V2 square by 4, Vn minus 1 square by 4 comma 0. Take A bar to be this, then you can see that A bar plus T times V is exactly these guys. So it contains a line in every direction. That part is easy to see. So what remains is to see this claim. Number of perfect squares.
X and Fq and minus x both map to the same element, and x and minus x are distinct because characteristic is not.
Okay. So what you are saying is, look at the map Fq to Fq, which Fq minus 0 to Fq minus 0. That is Fq star to Fq star, which sends the element A to A square. So psi maps A to A square. What you are saying is both A and minus A map to A square. Why can't any other element map to A square? but that will only argue that at most that many are squares. That's enough, but I want to argue that exactly that many are. Why can't more elements map to that? That's because, sorry? Yeah, so let's call this element a square as b, and suppose the pre-image is many of these guys, a1, a2, maybe all of them map to b. That would mean you look at the polynomial x square minus b, how many roots does it have? A1 is a root, a2 is a root, etc., ak is a root. How many roots can it have? Can have at most 2 roots. And you have said that it has at least 2 roots, a and minus a, 2 distinct roots. So they must be all the roots. Therefore, every element, every point in the range has exactly 2 things, 2 pre-images. So precisely half of them are squares. Yeah, good. Fine, that completes a construction that I wanted to describe. Okay, let's quickly, the next 15 minutes, see how to improve this to 1 by 4 power n. It's an interesting exercise. So I want to prove a larger lower bound than 1 by n factorial times q power n. Q power n is much larger than 4 power n. Okay, so let's erase the old proof. So this is a new idea which is involved in it, and it's got a different name. It's called the method of multiplicities. And the point being that if you give me a polynomial, a univariate polynomial of degree d, then I know that the number of distinct zeros that it can have is upper bounded by the degree. But it's also true with multiplicities. If every 0 has multiplicity k and the polynomial has degree d, then I know it can have at most d over k distinct zeros. So if you count the multiplicities as well, then you get a better bound on the number of distinct zeros. You want to use that, better, stronger counting argument basically. So in the case of univariate polynomials, we know what multiplicity means. It's simply the number of times x minus a occurs as a factor of the polynomial f. If the highest power of x minus a that divides f is k, then the root a has multiplicity k. In the multivariate case, how do you define multiplicity? So suppose G is a polynomial in fq x1, x2, xn, then and a is a 0. So I know that G of a bar is 0. What is the multiplicity of a bar? It's a natural definition. What you simply say is that you look at the multiplicity of G of a bar is defined as follows. You take the polynomial G of x bar plus a bar. I mean, replace x1 to xn by x1 plus a1, x2 plus a2, xn plus an. In this polynomial, what is the 0 that corresponds to a bar? It is the all zeros vector. For the all zeros vector, you can talk of the multiplicity in a very natural way. Go back to the univariate case. What is the multiplicity of the all zeros vector? All zeros of the 0. If 0 is a root, what is the multiplicity of 0 in a univariate polynomial? So, if 0 is a root, I know the constant term is not there. If 0 is a root with multiplicity 2, then I know both the constant and the linear terms will not be there. So, the least power of x that occurs in it will be 2. If it is a multiplicity k, then the least power that occurs in it will be k. We just generalize that and say the multiplicity is that in this polynomial, all monomials. So, if the multiplicity is m, if all monomials in g of x bar plus a bar have degree greater than or equal to m, and there is a monomial non-zero monomial of degree m. If there is a non-zero monomial of degree m, everything less than degree m is 0, then you say its multiplicity is m. And then we have a simple generalization. So, here is a lemma which says that if cardinality S is less than q power n by m plus n minus 1, choose n. Then there is a non-zero polynomial g such that degree of xi is at most q minus 1 for all I, and for all a bar in S, a bar is a 0, or let me simply say multiplicity of g a bar is at least m. If S is that small, then I can construct a non-zero polynomial which not only vanishes at all the points in S, but each of the points in S has that much multiplicity as well. Proof is straightforward, it is just 2 lines. See, for you take any point a bar in S, I want multiplicity of g a bar to be greater than or equal to m. So, what is the condition I need to impose? The coefficient of every monomial of degree at most m minus 1 is 0. The g's coefficients at a bar, every coefficient of multiplicity of degree at most m minus 1 is 0. How many monomials are there of degree at most m minus 1? M minus 1 plus n, choose n. Okay, there are, so m plus n minus 1, choose n constraints. What are those constraints? Take g, evaluate at a bar, the coefficient of every monomial of degree at most m minus 1 equal to 0. Each such equality gives me one constraint. That coefficient equal to 0 gives me one constraint. So, there are so many constraints for every point. Total number of constraints, is cardinality S multiplied by m plus n minus 1, choose n, which is less than q power n. I am only interested in a non-zero polynomial where every individual variable's degree is q minus 1. How many monomials are there? Every variable has degree q minus 1. You have q choices for every variable, 0 to q minus 1. Q power n monomials are there. Number of monomials is more than number of constraints, so it has a non-zero solution. So there exists such a polynomial. Now let's come to the proof. Again by contradiction. Suppose cardinality S is less than q power n by 4 power n. Now this is less than q power n by, I am going to take m equal to n here, m equals n in lemma. Because 4 power n is more than 2n minus 1 chosen. So what does it tell us? It means there exists G such that degree of xi is at most q minus 1, and for all a and s, multiplicity of a and g is at least n. Okay. And now I will use the fact that it is a Kakeya set, it contains a line in every direction. S contains a line in every direction. So I know that G of A bar plus V bar is 0 for all T in FQ. Now, look at this polynomial. See, this is a 0 of multiplicity at least n. It is a 0 of multiplicity at least n. What can we say about, say, every root of t gives me a point in the Kakeya set. It is a particular a bar plus t v bar. If I take a value of t, that is a point in the, gives me a point in the Kakeya set. What is the multiplicity of that root in the univariate polynomial h a v? H a v is a univariate polynomial in t. Every root of that gives me an element in the Kakeya set. It is a bar plus t v bar. The multiplicity at least n. It just inherits that property from G, because each of these guys has multiplicity at least n, because a bar plus t v bar is a point in the Kakeya set. It will mean that the corresponding value of t will occur with multiplicity n. What is the degree of h? degree of h is what is the degree of h? Q minus 1 into n is at most q minus 1 into n, because there are n variables, each one of them has individual degrees of each of them is q minus 1. In this construction we only ensured that the individual degree of each of the xi's is q minus 1. Okay. So the degree is this much, but each root occurs with multiplicity n. I have q roots, each of them occurring with multiplicity n. That means, but I know that so which is less than q times n. Each of the elements of fq is a root with multiplicity n. So this can happen only if h is identically 0. H is identically 0. This can happen only if h is identically 0. What does that give us if h is identically 0? The coefficient of t par d is gd of v, the homogeneous leading part again. It means, so h of this looks like t par d times gd of v bar plus. So this means gd of v bar is 0 for all v bar. But gd in every variable has individual degree at most q minus 1. Now the Alon-Tarski lemma that we did along with the Schwartz-Zippel test, what was that? Yeah, if the individual degree of each variable in a polynomial, maximum individual degree is say d1, d2, dn, and I take sets s1, s2, sn, where s1 is of size 1 more than the degree, d1 plus 1, d2 plus, and in that Cartesian product there must be a point where it is non-zero. In this case, take your set s, s1, s2, sn, all of them to be fq. Fq has q elements in it and the individual degrees are all q minus 1. So there must be a point where it doesn't vanish. Okay, this contradicts. So by Alon-Tarski lemma, there exists a v bar in fq power n such that gd of v bar is non-zero, because degree of xi is at most q minus 1 for all I. Let's just go over the entire thing once. Simple, three simple pieces. The key new idea is this: to construct polynomials with the zeros occur with larger multiplicity. So we want to prove that any Kakeya set inside fq power n must have this much size. Okay. We defined the multiplicity of a 0 in a multivariate polynomial. You just consider g of x bar plus a bar, and if all monomials are of degree at least m, you say that the multiplicity is m. The largest m with this property is the multiplicity. So there is a monomial of degree m, nothing less than m is there. What we can do is, so this is a very specific lemma. It says that you can construct a non-zero polynomial g where individual variables degree is at most q minus 1, and every element of such a set S, which is small enough, occurs with multiplicity m, and the proof is the same as before. Each constraint of this kind as so many linear constraints on the coefficients of G. The number of variables is q power n, which is more than the total number of constraints. Okay, so then you take this and plug it into your constraint that in every direction there is a line that is contained inside the Kakeya set. The fact that every point of the Kakeya set is a 0 of G with high multiplicity tells you that each element of Fq is a root of this polynomial HAV with high multiplicity. Okay, that is what forces the polynomials HAV to vanish. And once that vanishes, you simply pick the coefficient of T power D. D is the degree of G, total degree of G. And that must vanish at all the points. But that is not possible because individual degrees of the variables in GD is at most q minus 1. By Allen-Tarski, that is not possible. So again, subtle variations of the polynomial method. You count multiplicities as well, and then you can use that to get better bounds on the sets. Okay. Let us stop for the day. There is something that I wanted to write down for those who are interested in the Schwartz-Zippel lemma and applications. Here are a few papers that you might want to